Professor Clements with you as we discuss the mass spectrometer. It's a nice little exercise to review some of the concepts of electric field and then magnetic field. So this particular mass spectrometer, and I've sketched it down below our words here, has a velocity sector region, and I've represented magnetic field and electric field. The electric field is up the page of the paper with 736 volts per meter. The magnetic field is coming out of the page towards the camera here, upward, 3.2 times 10 to the minus 2 Teslas. It turns out that these fields are going to create a net force of 0 for certain chlorine atoms that have the proper velocity. And we want to know what is the magnitude of that velocity. Well, first let's investigate how can the force add up to 0. Well, if we take a look at this charged particle, it's positive. The atom has lost one electron. It's been ionized one time. And in the electric case, the force due to the electric field is the charge times the value of the electric field, and the force is in the same direction as the electric field. So the force for the electric field on this charged particle will be up the page. For the magnetic force, of course, it's a little bit more complicated. The force is Q, velocity, and there's a vector cross product with B, and that simplifies to Q, V, B sine theta for the size of the force, plus, maybe not even plus, but just as a side analysis, you must use the right-hand rule to find the direction of the force. The electric case is a little easier. We get the magnitude from Q times E, and we get the direction from the electric field. Magnetic forces are a little bit more complicated. We need to use our right-hand rule to come up with the answer. So let's think of the right-hand rule here. So we have our velocity for the charged particle off to the right. I would start with my fingers in the direction of the velocity, so that's step 1. Then I rotate my wrist so I can easily bend my fingers into the direction of the magnetic field, that is upward. The magnetic field is upward. I look at my thumb that's perpendicular to my fingers, and what I find is my thumb is pointed down the page like this, and yes, we do have the opportunity for the electric force to be balanced by the magnetic force. These two are giving us the same value of force. Further, let's investigate the theta here. That's the angle between the velocity and the magnetic field. Velocity is in the page, magnetic field is coming straight up the page. So we've got 90 degrees, I should say out of the page, for the magnetic field. And the sine theta will be 1. So we get, in terms of magnitude, the electric force, Q times E, is equal to the magnetic force, QVB, and the Q's cancel. It doesn't matter if it's been ionized one time or 2 times. For this one object, it'll have the same Q in both of these calculations. And our velocity, I can solve for velocity and find it's the strength of the electric field divided by the strength of the magnetic field. We have those numbers, 736 volts per meter. I need to slide up a little bit. So electric force equals magnetic force. Eliminate the Q's. The velocity, where the force is equal, take electric field divided by magnetic field, 736 volts per meter, and 3.2 times 10 to the minus 2 Teslas for the magnetic field. You should stop and do this calculation on your own calculator. But what I came up with, now after you've restarted the video, 2.3 times 10 to the 4th meters per second. That will be the speed of the ions that are able to go straight through and now enter the right side of the mass spectrometer where there's only magnetic field. Some concepts here. If the velocity is higher than this number, the magnetic force is going to be higher than the electric force, and the object will bend down and miss the opening, the narrow opening. If the velocity is smaller, then our magnetic force will be smaller, the electric force would dominate, and the particle would hit up above the opening. So we have this velocity for the ions coming into the magnetic field region where there's only magnetic field. All the isotopes have this velocity, all the ions have that velocity. Now let's suppose in our chlorine beam there are two isotopes of chlorine, and chlorine 35 has a mass of 5.793 approximately times 10 to the minus 26. Chlorine 37, two more neutrons in this chlorine atom, same number of protons, that's what makes it chlorine, a certain number of protons, but a higher mass because of the extra neutrons, 6.137 times 10 to the minus 26 kilograms. And we want to know, at the impact of the ion beam with our detector wall, what's going to be the spacing of where the chlorine 35 ions hit and where the chlorine 37 ions hit. Now, to analyze our motion in here, I tried to draw a semicircle. It is circular motion, and for that circular motion the magnetic force is supplying the centripetal force. The magnetic force is QVB. The factor of sine theta is a 1. Our velocity is perpendicular to the magnetic field, so the sine theta is sine of 90 degrees, and our centripetal force is mv squared over r. I can cancel one factor of the velocity on both sides, and if I solve this for r, we get mv over qb. It's our expression for calculating the radius of the circle. We're moving on a circle for the ion in the presence of this magnetic field. We're going to calculate the radius. The impact point is a diameter away. So once we calculate the radius numbers, then we'll multiply them by 2 to get diameter. And then we'll subtract those two diameters. I'm not drawing the second path just because I don't know if I can draw as good a circle as I did for the first one. But let's look at this calculation. The radius would be the mass of the ion, and for this particular problem our velocity selector has given us 2.3 times 10 to the 4th meters per second. And there's a reason why I'm not putting in the mass right now. The charge, if we ionized one time, then 1.6 10 to the minus 19 coulombs. And our magnetic field has a value of 3.2 times 10 to the minus 2 teslas. We need to do this calculation twice, once for each isotope. So I'm going to go ahead and do the things that are constant first. Velocity divided by Q divided by B. And you ought to check this on your own calculator. Pause now if you wish. But the V over Q over B I found was 4.4922 times 10 to the 24th. And now if I do this for the chlorine 35, the radius, go ahead and put in the proper mass here. For chlorine 35, you're putting in 5.793 times 10 to the minus 26. Substitute that in for the m here and multiply. The radius I came up with for chlorine 35 was 0.2602. And again, you ought to pause and check with your own calculator. Oh, the diameter, if I double that, roughly 0.5205 meters. Then we repeat the calculation with chlorine 37, the other isotope. Now you have to recover the mass of that isotope, 6.137 times 10 to the minus 26. Put that into the value of m, multiplied by the pre-done evaluation of velocity divided by Q divided by magnetic field. And for this situation I came up with 0.2757. Do you think it's reasonable that this radius is larger? Yes, there's more mass here, there's more momentum, more inertia, and it's more difficult for the magnetic field to create the circle. So the things that have more mass go in larger circles. You can see that mathematically here. If m gets larger, r gets larger. And the diameter, if I double this radius, roughly it's 0.5514. If I subtract these two numbers, I find that the difference in the impact location is 3.09 times 10 to the minus 2 meters, or 3.09 centimeters. So these two chlorine isotopes can be separated, can be analyzed. 3.09 centimeters will be the spacing of their impact points in this mass spectrometer. And if you have detector equipment here that's able to detect how many impacts have occurred, what you'll find is that roughly 76% of the impacts occur for the chlorine-35 position, and about 24% of the impacts will occur for the chlorine-37. There is a relative abundance of chlorine isotope, and the chlorine-35 is the more abundant isotope, so it'll have a darker spot on your detector. So there's the example of mass spectrometer. We have a velocity selector. We balance electric and magnetic force. We can calculate then the velocity of the ions that will go straight through when the force is balanced. If the velocity of the ion is different than this, it will not enter the second region. It'll hit above or below the opening. So we have a known velocity for the calculation here, and that enables us to calculate the radius. Given mass, once ionized, magnetic field value for the region, we can calculate the radius. It depends on the mass of the isotope. It's a mass spectrometer, can reveal to us the mass of the ions that are traveling through.